Alright, this is lesson 1.1.1, Mechanisms, Simple Machines. There's 6 types: lever, wheel and axle, pulley, inclined plane, wedge, and screw. There's 2 parts to the mechanical advantage of these different types of simple machines. The first part looks at forces, and it's the ratio of magnitude of the resistance and effort forces. The second part looks at distance. It's the ratio of distance traveled by the effort and the resistance force. So we look at simple machines and what kind of work they're producing for us, and we look at the efficiency. So first we look at the type of work that these simple machines are going to do, and we're going to look for something to put these numbers into perspective. So we're going to look at force and distance, and with principles of engineering, we're going to look at some different types of delimitors that you may not have seen before, and in this case, this formula is let's see my mouse here. Force times distance, and you'll see this new 2 vertical lines, and that designates this variable as distance. So there's going to be a lot of new things that we're going to see. A lot of it will go with the conventional logic that we've learned in our previous math classes, but there's going to be some stuff that is very specific. The types of math equations you're going to see is going to be very specific to this course, and so you just have to put that in your memory. You're going to see some different kinds of symbols that you've never seen before. Alright, so we're going to look at mechanical advantage ratios. 1 is the magic number. Alright, so if your machine is easy to use, you're going to have a MA of greater than 1, a mechanical advantage greater than 1. Proportionally less effort force is required to overcome the resistance force, and secondly, proportionally greater effort distance. So the more distance you put between you and the resistance, the easier it's going to get, and the less effort is going to be required to overcome the resistance. Alright. If your mechanical advantage is less than 1, proportionally greater effort force is required. So it's going to be more difficult. And proportionally less effort distance is required to overcome the resistance force. So you're going to get closer and closer to the object that's providing that resistance, and you're going to have to apply more force. MA can never be less than or equal to 0. You're always going to have some kind of mechanical advantage. Alright, there's 2 types of mechanical advantage. The first type deals with distance. You saw with the previous slide, as we go up, we have greater distance. As we go down, we have less distance. So taking distance into account is necessary to figure out just what's going on with the need for distance in between you and the resistance force. So when you're looking at distance, friction is not taken into consideration. We're just looking at the numbers, ratio of distance traveled by effort and resistance force. That's all we're looking at. And there's your formula. Now you're going to have to, it's going to be memorization. You're going to have to memorize this because this is going to be something we're going to use all year long. IMA, ideal mechanical advantage, equals distance effort divided by distance resistance. So the distance of the effort. So when you're pushing down on a lever, you are the effort. The resistance is whatever you're trying to pick up. So the distance between you and the fulcrum is the distance effort, and the distance between the fulcrum and the resistance is the dr. So the fulcrum is the pivot point, and we're going to get into that here in a few more slides. All right. Distance traveled by effort force, distance traveled by resistance force. Okay. All right. Actual mechanical advantage. Part 2 of trying to figure out your how efficient your machine is, your simple machine. Friction is taken into account, used in efficiency calculations, the ratio of force magnitudes, actual mechanical advantage. We're looking at force, not distance. We're looking at force. AMA equals force resistance, FR, divided by force effort. And we can swap those back and forth depending on which numbers you're looking for. And what do I mean by that? If the axle is driving the wheel or the wheel is driving the axle, there's different needs to swap those out. And you'll see what I mean here in a few slides. So FR equals magnitude of resistance. I'm reading off the bottom. Magnitude of resistance force. FE equals magnitude of effort force. And after we work through a few problems, a lot of this is going to, I found it's easy to understand. FR stands for force resistance, FE, force effort. A lot of it does make sense. You may have not seen it before, but it's going to make sense. All right, real world mechanical advantage. Can you think of a machine that has a mechanical advantage of greater than 1? Something that's easy to use. Windmill. If you ever drive down to Corpus Christi, you'll see the windmill farm off to the left if you're about 10 miles out, and you'll see that windmill farm. All right. Another example is inclined plane. Machine with a mechanical advantage is greater than 1 multiplies the input force. So anything that multiplies input force can open a ramp, windmill. All right. So can you think of a machine that has a mechanical advantage of less than 1? Think about something that's difficult to use. Maybe something it's created on purpose for its difficulty to use, and that would be gym. So it takes a lot of force to overcome the resistance, and that's done on purpose. All right, so levers. So this is basically step 1 of understanding mechanical advantage. And it's a rigid bar used to exert pressure to sustain a weight at one point, and the fulcrum is the pivot point. In this case, it is the pyramid at the middle and at the end. All right, so the top middle animation is the force effort is the left gold arrow. Force resistance is the blue arrow, and in that case, the fulcrum is in the middle. Bottom left animation, the force resistance is blue. It is in the middle, and that is going to be a mechanical advantage of greater than 1. The one on the left, because the effort is, or the resistance effort is, or resistance force is in between the fulcrum and the effort. Bottom right animation, the force resistance, force effort is, actually that's force resistance, I'm sorry. Force resistance is on the outside of the lever, and that is going to be a mechanical advantage of less than 1. So the one on the right is harder than the one on the left. Alright, let's make sure that looking at this, I'm just looking at the bottom illustration here. I've got okay. Alright, I was just making sure that I didn't make any mistakes in describing the previous slide, and I did that correctly. Alright, so we have 3 kinds of levers. First class lever, the fulcrum is located between the effort and resistance. Effort and resistance forces are applied to the lever in the same direction. So, let's say first class lever, a playground seesaw would be one example. And the mechanical advantage can be greater or less than 1, either or. So the middle, top middle, mechanical advantage is in equilibrium, so that your lever is level. Bottom left, we have shortened the. Let me bring up the. Hold on. Bring up our definitions. All right, so bottom left. So the distance between our effort, that's the gold arrow. It's kind of gold, I guess. The distance between the effort and the fulcrum is short. Your resistance is way out on the end. So according to the definition at the right, mechanical advantage of less than 1, you're going to be closer to the fulcrum, and it's going to require a lot of effort to overcome that resistance. Bottom right hand illustration, you can see that we've increased the distance between the fulcrum and the effort, so our mechanical advantage is greater than 1, and that matches up with our definitions at the right that I brought up. Alright, so our second class lever are 2 of 3. Fulcrum is located at one end of the lever. Okay, and resistance force is located between the fulcrum and effort force. And I can already tell this looks exactly like a wheelbarrow. You got your wheel at the end, you got your dirt in the wheelbarrow, and you are picking up on the end of the handles. That's basically a mechanical advantage of greater than 1. So that's a second class lever. Third class lever. Fulcrum is located at one end of the lever, just like second class. But this is probably the least favorite type lever. Let's see here. Every force is located between the fulcrum and the resistance. Resistance from force and effort. Force they're in opposing directions. So both 2 and 3 are in opposing directions. But third class lever is a mechanical advantage less than 1. Example of this would be, say in a mechanic shop, you have a pneumatic lifting jack. The pneumatics is going to be the effort, and the resistance is going to be either a car engine, something like that. So you want to extend the lever above the car, put the chain on the lever, hook it up to the engine, and lift it up with pneumatics. That's basically those third class levers are pretty much all over the mechanic shop. Alright, I learned the hard way that this slide, if I don't spend enough time on this and tell you that this is an important definition, it will come back and haunt me when I decide to teach you guys. I think it's the third unit, which deals with calculating trusses on a bridge. So I covered this my first year teaching POE. I covered this, and we spent maybe 30 seconds on this, and I went on for the rest of the year, and around spring break we came back, and I said, remember, talked about the definition of moment, and no one had an idea what I was talking about. It's because I did not emphasize, maybe I didn't know from lack of experience, I did not know that this is a very, very important definition that's pretty much going to tie the entire year together. Okay, so moment. It's not a moment in time. It's how physics works in this class. Okay, so it's a turning effect of a force about a point equal to the magnitude of the force times the perpendicular distance from the point to the line of action from the force. Yeah. It's completely different than what you would think a definition would be, but if you go into the world of physics, this word takes on a whole new meaning. All right, so distance times force looks like a simple, straightforward formula, but let's fast forward 6 months and say, okay, if you have a bridge, is there just one force that's being applied to the entire bridge? No, there's hundreds. So this can get very complicated. So it's very important that we don't miss a beat when it comes to all the definitions. Okay, so moment, pretty simple. It gets complicated. Distance times force, torque. So not all machines produce torque, but in this case, it's a good starting point. The force that produces or tends to produce rotation or torsion. If you're looking at a bridge, there's probably only a couple points on that bridge that's going to create torque. Other 99% of the other points on that bridge are going to be stationary, but you're going to have some that produce torque, so you're going to have a complex calculation to figure out just how efficient that bridge is. All right, lever moment calculation. So now we've talked about the levers, the different kinds of levers, 1, 2, and 3. Now we're going into step 1 of understanding and getting the values you need to understand the mechanical advantage of this simple machine, which in this case is a lever. So the first thing you have to do is you have to calculate the moments. All right, and once again, it's distance times force. All right, so you got forces and distances on this example here. So you calculate the effort and moment acting on the lever. Distance times force. Pay attention to the fact that we're looking at the effort only. This is the effort. We're not looking at the resistance. We're looking at only the effort. All right, so the effort moment is distance from the effort to the fulcrum is 5.5 inches. The effort is 15 pounds. So you're putting 15 pounds of pressure on that to overcome the resistance. All right, so now we're looking at this is where we're going to kind of divert a little bit away from the normal train of thought of, hey, you've got to keep like terms together, like units together. This is where we kind of divert just a little bit from the traditional sense of like units, grouping them together. We're multiplying inches times pounds. Okay, So keep that in mind, because if you don't have the right unit of measurement at the end of your calculations, you might have the right number, but it's not going to be the right unit of measurement, and it has to be that process you go through to get the right unit of measurement. And so if you just watch what you're doing, it'll all come out correctly. All right, so 5.5 times 15 is 82.5 inches pounds. And let's take the, okay, I'll leave that up. Leave the definitions up on the right-hand side there. So it's 82.5 inches pounds. I didn't say inches per pounds, I said inches pounds, and that sounds strange to say that. I say, well, is it inches per pound? No, it's inches pounds, okay? So keep that in mind when we go to, we're going to look at this real quick. It's not part of this example, but it's when the sum of all moments on a lever equals 0, it's in rotational equilibrium, meaning the lever's not going to be moving. Rotational equilibrium is clockwise moments and counterclockwise moments add up to 0. All right, so back to our lever. So we added a value onto the resistance side of the lever, 36 2/3 pounds. So now, looking at the definition before, we want to make rotational equilibrium. So if we want to set everything to equal 0, or we can set, in this case, 0 meaning this lever is balanced, and visually the lever is balanced. So in theory, if it's balanced, it's in equilibrium, and so we can set them to equal each other, and the variable will come out to what we need to create that balance. So we took our calculations and our measurements from the previous slide, 2 slides back. We got 82.5 inches pounds. There's that dash. It's not inches per pound, it's inches pounds. Equals 36.66. They just converted that to decimal to make it easier. There's my variable. My distance resistance. I don't have my distance. My dr is my variable. That's my question mark. Okay. So 82.5 inches pounds divided by 36.66 pounds. This is where you cross out, cancel out the pound unit measurements, and you're left with inches. So the distance resistance equals 2.25 inches. 2.25 inches, and that's your dr. So you've solved the lever moment calculation. Now back to mechanical advantage. So you've got all your variables answered. Everything is known. And so we got to get into mechanical advantage. We need to see, is this, or what is the percentage of efficiency that we have with this lever? Is this the best kind of lever we can have? Can we do better? No way to find out just off force and resistance. We have to know, does it have a mechanical advantage of greater than or less than 1, or is it an efficient lever? All right, let's see. All right. So rotational equilibrium, the effort force counterclockwise is equal to the resistance movement counterclockwise. All right. So now we are going to look at mechanical advantage. All right, so we've calculated the moment. Now we're looking at mechanical advantage. All right, so IMA, and yes, I have my definitions there up on the screen. IMA is distance effort divided by distance resistance. All right, so in this case we have this is an example of torque. It's got a rotational, it's traveling in a rotational path, both effort and resistance. So this is my circumference of my resistance. My circumference of my effort is the outer circle. So circumference is the distance around the perimeter of the circle. Okay, circumference equals 2 pi r. So IMA is my distance effort right here divided by my distance resistance right here. That's going to be my IMA. Okay. So effort arm length, resistance arm length. Okay. All right. Lever AMA. Hold on a second. All right. So we're going to actually calculate in a couple more slides. All right. So lever AMA. Force resistance is 32 pounds. That's going to be on the top, and force effort is 16 pounds. So it's going to be 32 divided by 16. AMA is a ratio of 2 to 1. What is the IMA of the lever above? Okay, so the previous page, the reason we didn't do the calculations is because they wanted you to have the advantage of doing all the calculations on one page. All right, so what is the IMA of the lever above? Distance effort is 5.5. Distance resistance is 2.25. And you can see we would not have that number if we did not calculate our moment and get that left side equal to right side and get that variable answered. We couldn't do this step right here. Okay. So you have to go in sequence. All right. So 5.5 is your distance effort divided by 2.25. 2.44 to 1 is the ratio. Why is the IMA larger than the AMA? That's something you need to think about. All right. So efficiency. We want to know how efficient this lever is. So it's AMA divided by IMA. Get the previous calculations that we just did, which is 2 to 1, 2.44. So 2 divided by 2.44 divided by, or multiplied by 100 gives you an efficiency of 82%. So if you adjust the numbers back and forth on force versus distance of resistance and effort, you can bring those numbers up and down depending on the work that you need to do. No machine is 100% efficient. There's always room for improvement. Okay, let's switch to wheel and axle. A wheel is a lever arm fixed to a shaft called an axle. It helps lift or move an item by rolling. Pretty simple, straightforward. Your effort's going to be if the axle is driving the wheel. In this case, that would be the purple would be the effort, and the resistance would be the blue. If the wheel is driving the axle, the other way around, the effort would be the blue, and the resistance would be the purple. All right, so here's an example. I know I went a little too fast. These are wheels driving axles. All right. All right, wheel and axle IMA. All right, so Okay, both effort and resistance forces will travel in a circle if unopposed. Circumference equals 2 pi r. There's other ways to calculate. There's another way to calculate circumference, but we're going to stick with 2 pi r. IMA equals effort over resistance, and we're going to cancel out the pi, and we are going to plug our values in. Okay. All right, what is the IMA of the wheel if the axle is driving the wheel? So the axle is going to be my effort. And if you go up here, the effort would be on the top there. So that would be 6 divided by 20. And right here it's 0.3. You don't want a decimal. You want a whole number in the ratios. So you move the decimal to the right 1, which moves this to the right 1, which would be a ratio of 3 to 10. What is the IMA of the wheel if the wheel is driving the axle? In the case of car steering wheel. So we're just going to flop those. Flop or switch those so that the resistance is going to be above, effort is going to be below, and then you're going to have a ratio of 3.33 to 1. Wheel and axle AMA, force resistance and force effort. I believe we're going to be consistent. We're going to in the last, we're going to stick with wheel driving the axle, I believe. Next slide here. Or we might just go with both examples. All right. What is the AMA if the wheel is driving the axle? As in our second example in the previous slide. So if the wheel is driving the axle, then your effort, let's see here, effort is going to be on the bottom, and your resistance is going to be on the top. Okay. All right, and then what is the efficiency of the wheel and axle assembly? So your AMA is going to be, or your efficiency is going to be AMA divided by 100, or divided by IMA times 100, which is 2.86 divided by 3.33 times 100, which is 86%. So it's important to know these formulas for AMA and IMA. There may be a need to solve for force resistance or force effort, swapping these things around. But we're just going through some simple, straightforward examples. But as it gets more complex, they may not give you all of the answers, and you're going to have to move that formula around to fit the situation. All right. Okay. So we're going to go into pulleys briefly here. It changes the direction of the magnitude of force exerted by a rope or a cable, and illustration on the right is a fixed pulley, first class lever with an IMA of 1. Changes the direction of force. Illustration on the left. It's a movable pulley, so the one on the left, the pulley is going to go up and down, and it has an IMA of 2. Force directions stay constant. Okay. All right, so pulleys in combination, fixed movement pulleys combination called block and tackle. We used a lot of this stuff when I was in the Navy. Provides mechanical advantage in the change of direction of vector force. A single rope or cable is threaded multiple times through a system of pulleys. Pulley IMA equals number of strands opposing the force of load. Alright, so if you can see the illustration as I go click back and forth, it shows you which strands are opposing the force, and that is these four right here. This one's not opposing. This is your effort strand. These are the ones that you're gonna count for IMA. All right, compound machines. Compound machine is anything where you put two machines together. In this case, you have a pulley system and a lever. All right, so you have to figure out the IMA, AMA efficiency of this compound machine by combining your measurements. Okay, so IMA total equals IMA pulley. You have two strands. This symbol right here is a fixed point, so that these both are going to be providing the, what's it called, opposing force on the load. Alright, so then IMA pulley, number of strands, equals 2 times IMA of a lever. Remember, IMA is, I believe I have my definitions over there. IMA of a lever is distance effort divided by distance resistance. Distance effort is 12 right there. From here to my fulcrum is 12. My distance resistance is from fulcrum to resistance is 4. 12 divided by 4 is 3. 2 times 3 is 6. So my IMA total is 6. Pulleys in combination with separate ropes and cables. The output of one pulley can become the input for another. All right, so the number of strands, we've got 1, 2, 3, 4, 5, 6. Or 2, 2, 2. And then we're going to multiply IMA total equals IMA 1 times IMA 2 times IMA 3. 2 times 2 is 4 times 4. 4 times 2 is 8. So we have an IMA of 8. All right, pulley AMA. All right, so we have AMA is force resistance over force effort. So what is the AMA of the pulley system on the right? Force effort is going to be 230. Force resistance is going to be 800, so 800 divided by 230. Pounds cancel out, so you have a 3.48 to 1. What is the efficiency of the pulley? AMA 3.48. I forgot what number we got for the IMA. Oh, it's 4. 3.48. What am I talking about? Yeah, I temporarily lost track of what I was saying. Okay, the 4, not from a previous screen. The 4 is from this screen, which is 4 strands. 1, 2, 3, 4. Actually, this same block and tackle was used about 3 slides ago, but you have to make sure you update your mental thought process here. And yes, it says 4 strands. There we go. Okay, so 3.48 divided by 4 times 100 is 87%. Okay, so misconception, angles don't matter. They do. All right, so pulley IMA, number of strands opposing load only if strands are opposite and parallel. So pulley IMA, what we just did only deals with if they're opposite or parallel. If we have this kind of situation set up here, it goes into some advanced trigonometry that we're not going to get into for at least about a month or so. So we'll get into this, but we have to calculate the angles, and then we're going to combine it all together. And this is kind of what we're going to get into when we get into bridges and trusses and all that stuff. But let's not get ahead of ourselves. We're going to stick with what's on the left. And You got 2 strands, so IMA is 2. Okay. All right. Common misconception: count the effort strand if pulls up sometimes. All right. Pulley IMA equals number of strands opposed to the load. In this case, it's 2. And let's go back. That's it. All right. So pulleys, we're not going to get into a lot of those. It's good to know, but we're quickly going to go from here to here.